volt as an output. So this is just a trick. Yes, but of course there are different voltage regulator, voltage stabilizers. So this is the series of 317. And in this case, we can set the output stabilized voltage using two resistors as an output. Okay. Okay, so that was the simplest solution is then if we've got the input voltage higher than the output voltage, because you could see that we've got 12 volts here and 9 volts here. Generally, this kind of regulators have a voltage drop between the input and output is more or less 2 volt, 1.2 volts. Yeah, there is a series of low drop regulators, and then they have, let's say, 5.5 volts of voltage drop. So generally, we need a higher voltage of the input, and we can achieve lower voltage as an output. Okay, it's a solution, but the problem starts when we are going towards mobile elements, mobile circuits. Yeah, so we would like to use small battery and have the possibility to achieve higher voltages. For example, we can use a lithium battery which have 3.5, 3.7 volt, and we would like to use it to supply a microcontroller or something like this, which probably could have 5 volts as an input. So this is the problem, that we have lower input voltage and we would like to have higher output voltage. What to do in this case? We now going into the group of circuits which are called switch power suppliers. Yes, switch such a circuit. So this power supply is using switch modes. Are nowadays very common. You can have it everywhere, from the supplier to for your mobiles to the computers. Also nowadays they are everywhere because they change the thinking about voltage regulators. Okay, they are smaller, they are more efficient, they are quiet, so we do not need to use a very heavy transformers on so. But how? So from the definition, the switch mode power is a type of power supply that uses semiconductor switch techniques. So we suspect that we've got some switching. I'm sorry. So we've got a transistor which switches something. You will learn what the transistor switches. So we use rather the switching than the linear method of voltage regulators. So generally the basic switch converter consists of a power switching stage and a control circuit. So we have some elements for switching and some elements for control the switching. Okay. So the power switching stage performs the power conversion from the circuit's input. Yes, so we've got the input voltage and it converts to the output voltage. Because it is a switching method, so generally the output should be filtering, because they will another way will have the spikes and the voltage will be not stable because it is switching. So we need filtering of the output voltage. The first topology, because we can say that we've got different topologies of the switching voltage regulator. So I would like to start with the topology which is called boost switching regulator. From the name of the boost, yes, boost, it means that we increase the voltage. Yes, so we suspect that the input voltage is lower than the output voltage, and in this case we use boost switching regulators. Yes, this is the type of regulator that we use: a coil and a switching transistor and capacitor. And okay, maybe in this moment I will show the film, because maybe it will explain better than me. Can you see the film? Yeah.
Yes.
Okay, thanks.
Suppose we want to increase the voltage of our only battery. We have an inductor, a transistor, a diode, and a capacitor.
Okay, so the simplest switching regulator consists of the capacitor, of the inductor, and the switching element. Of course, we need a source of power and the output load.
We also have a device to which we have to deliver power, represented here by a light bulb. The connection to the gate of the transistor is not shown, but this is a voltage that we control. Suppose we control this gate voltage in a way such that the transistor behaves like a switch, which we can turn on or off. If we close the switch, we will cause a DC voltage to appear across the inductor. The current through the inductor will keep increasing so long as the switch is closed. The current through an inductor cannot change instantaneously. Therefore, the moment we open the switch, the inductor will create a force causing the current to continue flowing. Suppose we keep turning the switch on and off. By continuously turning the switch on and off, we have created a DC output voltage at the light bulb that is higher than the voltage of the battery. We call this a boost converter. We can control the value of the DC output voltage at the light bulb by controlling the percentage of time that this switch is on. Suppose that we leave the switch off all the time. With the switch off 100% of the time, the output voltage will equal the voltage of the battery. What if we instead have the switch on most of the time? If the switch is almost always on, then assuming we have ideal components, the current will theoretically keep increasing to infinity. During the brief moment when we turn the switch off, an infinite current would charge the capacitor to an infinite voltage. By selecting the appropriate percentage of time that the switch is on, we can set the output voltage to any value that is larger than the battery voltage. But we will need a different circuit to produce a steady state output voltage that is smaller than the battery voltage. At first, this may seem simple, as this can be done by using resistors to create a voltage divider.
Okay, so that was the situation when we've got a boost switching regulator. This is the circuit. So when it's on, we accumulate energy on the coil, yes, and we switch it off. We transfer this energy into the capacitor. So in this case, because the voltage here will be higher than the voltage on capacitor, we will load the capacitor, and in this case, we will achieve higher voltage than the input voltage. Okay, so generally we can say that the output voltage is the input voltage multiplied by 1 minus duty cycle. Yes, duty cycle, it is the time, it is the difference, not difference, this is the switch on time to switch on and switch off time. Okay, so generally the D is lower than 1, so in this case we will have higher voltage, a higher output voltage than the input voltage. Okay, so what are the advantages of this, such a circuit of switch mode power supplies? It is the high efficiency, because all the current which is accumulated on the coil is going to the capacitor. Yes, of course in this topology, because we will discuss different topologies. But generally, in this case, we have very small losses, energy losses, because, as I said, all the energy of the coil goes to the capacitor. The problem, of course, is from how to steering the transistor, the control circuits is very important, but it will be later. So generally, we've got two states. One is this on state, when it's saturated, and one when it's off state, it is cut off and the energy goes from one element to another. So, and generally, we can of course discuss an ideal voltage regulator, but in our life it's not possible to make an ideal one. Okay, so maybe I will make an experiment. I have prepared a circuit. Yes, this is this is okay. This is not this circuit, but okay. So that was the boost switch power. Yes, so this is that was the we could achieve higher voltages from lower voltages, but we can also make a different construction, which is called, that is topology is buck switch. Yes, this is buck switch mode power supplies, and this topology causes that we decrease the input voltage. So, for example, we've got 12 volt as accumulator, and we need 5 volts or 3.3 volts as an output. So, of course, we could use a linear voltage, but it is have lower efficiency. So we can also design a switch power supplier that decrease the voltage. You can see that we've got a transistor here, so it controls its on in have the position on and off, and changing this proportion from on and off time, we can change the amount of energy going to the coil and to the capacitor. And in this case, we will change the voltage as an output. Okay, so now this third circuit, yes, this is the circuit connected with the transistor, which switches on and off the circuit. So we've got a inductor and we've got a capacitor. Okay, so let's see what's happened here. This is, we can see the output voltage, and in this case we've got this switching control circuit. Yes, let's say it's for now it is just a generator. Let's say we've got 50% of the fulfill, so we've got the same frequency, the same time for the on and the off, and the frequency. How fast can we switch this circuit? Generally, we could switch it any frequency we want, but in practice, it is set more than 20 kilohertz. Why? Because we can't hear these frequencies. Yeah, so they generally the switching power supplies are set for the frequencies higher than can we hear. So maybe it's not 20 kilohertz is maybe not the best solution, but sometimes it's appeared 200 kilohertz and more. So we can't hear, because if we set lower frequencies, we could hear what happened on the coil. Yes, because it's something moving inside, so it makes some elements that we can hear. Okay, so generally we use higher frequencies, but in our simulation we use a bit smaller. Okay. Okay, so we've got a multimeter. Let's set also oscilloscope. We'll see what's going on the. Okay, so the blue line will show you us what's on the output, and the red Y will be show what is on the diode. Yes. So we suspect that if we set 50% of the for the control circuit, we should have achieved more or less half of the voltage. So we've got 12 voltage. Okay, let's start the simulation. What's happened when we can start? I don't know what's happened. It doesn't like me. I don't know what's going on. Okay, now it seems to kick. Okay. So you can see this is the switches phases. Yes. So the switch is on, yeah, switch is off, and the value on the output. Yes. So you can see that we've got more or less half of the voltage as an output. Yes. So in this situation, we decrease the input voltage by 2, yeah, more or less. Okay. So let's try to change the duty time. Yes, let's say 20%. So you can see that we decrease the output voltage 6 times, and this is because the on position is faster than the off position. So the time of on is lower than the time off, and in this case we can increase the duty time up to, let's say, 90%. And in this time we suspect higher voltage as an output. Yes, and this is the on time and off time. So the on time is longer than the off time, so we suspect more voltage, more power on as an output. And you can see that changing the duty cycle, we can regulate the output voltage. Okay, do you understand it? It's clear. Okay, thanks.
Yes, but I've got a question. We still have to somehow filter this signal, yes? Then
yes, of course. Yes. We need some capacitors, some filters, but it's different problem. Yes. So.
And those components, like LM or 7/8 series, are. I mean, they are this switch mode, or
no, they are linear. They are linear
okay.
regulators. So they have no high efficiency when we have to change the voltage, for example, from 12 to 3. So we have amount of heat on it. So we need to use some radiator, some more elements. Okay, so that was the 790 series. It's not switching regulators. Okay.
Okay, thank you.
Okay, so as you can see, we can control the output voltage, changing the properties of the control duty cycle. Okay, that is just to, you should know it. Okay. Okay, so the back mode power supply is a second topology we could achieve, and this is what we construct, and we can calculate the, if we said that the D is the duty cycle, so it's time on to total time, so the time on with time off. So this is the duty cycle with PWM regulators for PWM signal. So the output voltage equal to multiply by VIN. Okay, but the duty cycle is lower than 1, so we decrease the, in this situation we can decrease the input voltage. Okay. Okay, we've got another topology. This is the case when we've got the problem that our output voltage is, let's say, 3.3 volts, and we use, let's say, a lithium battery. Okay, the lithium battery, the voltages from the lithium battery is from 3.7, let's say, up to 2.4. So in this case, the output voltage is between our voltages on the input. Yes, so because it is variable. So in this case, we can use a construction, a topology, which is buck boost. From the name, we can suspect that we've got something that, in one case, increase the input voltage, and another case that can decrease the output voltage. And this is the topology. Yes, this is the topology that using different control system, different time on to off, we can change the output voltage in both directions. Yes, so once we can have increase the voltage, and we can decrease, or we can decrease the voltage. This is the equation. So in this case, we can see that that we can, because D is lower than 1, so we can change the voltages. Yes. The next topology, it is the CPEC switching regulator. This is from the name. Yes, this is the single-ended primary inductor converter. CPEC name. Let's say CPEC. It is a kind of boost back topology, yes, because it can step up or down the input voltage to a high or lower output voltages. Yes, so it can convert our voltage both for higher or lower voltages. And as for switching regulators, the energy is transferred through the FET, so MOSFET transistor. Yes, because MOSFET transistors are faster than the JFETs or the bipolar transistors. So we generally use MOSFET transistor to switch the coil, to switch the elements in the switching regulators. Okay, so this is the CPEC topology. In this situation, we've got 2 coils, because one coil corresponds to the buck converter and one for the boost converter. So if we change the proportion of the time on to time off, we can achieve higher or lower voltages as an output. Of course, as the students noticed, we need to filter the output signal. In this case, we've got just one element, but we could have more elements to filter the signals. Of course, we can use some inductor and capacitors as well here. Okay. The another construction, the another topology, it is a say CAC converters, CAC regulators converters. This is a positive input voltage to a higher or lower negative voltage. So we in this case, we can produce negative voltage. Yes, because in somehow you would like to switch to, for example, for the operation amplifier, we need to supply them from the pluses and from minuses. Yes, so we need a source of plus voltage and source of minus voltage. So in this case, we could achieve, yeah, because this is minus, we could achieve a minus voltage from the pluses. So we can construct a voltage regulator connect as a parallel connection with the CEPIC, yes, and then we have the pluses and the CAC, and then we have a minus. And if we connect them together, we will have the possibility to control, let's say, the operation amplifier with supplies with different voltages. Okay, so this is another topology. The next topology is this, the Zeta. This is the Zeta switch regulator. This is the regulator that also is a busboard type of regulator, but it consists also with two coils in a different position, and the capacitor is here to have some energy stored in the capacity. Okay, and so on. We can construct more and more complicated elements. So this is the flyback regulators. In the flyback regulators, we, instead of the coil, we use a transformer. In this case, we can achieve higher or lower voltages, depends on the number of turns on the transformer. So we can set for the beginning, yes, what is the connection between input and output, and then by regulating the current going from the primary coil, we can regulate in the smaller position. We can regulate the output voltage, both to make a higher voltage on lower voltages, because if the amount of turns will be lower here and more here, so we increase the voltage, and if we have more turns of coil here and lower here, we can decrease the voltage. Okay, this is the flyback switching regulator. We can construct something like two switch flyback regulators. In this case, we got two transistors. What does it cost? It doesn't cost that you can increase the frequency of the elements, because in one hand we can supply this coil, but if we use a transistor, we can make that it a faster discharge of the coil. Yes, because in the last examples, we just switch off the transistors and the coil was naturally switching off. And in this, we have something that you can make the faster. Yes, so we can use higher frequencies and more efficiency regulators. Okay. Another type of the topology of the switching regulators is the active clamp forward. This is we can use a transformer here and two switching transistors, and it's similarly, these transistors, one is for fill the coil with the electromagnetic flux, and another is to switch it off and cross the and make the faster to have higher frequencies for this and higher elements. Okay, this is another topology. This is single switch forward, and so on. So we've got a lot of topologies. Yes, this is the forward switch regulators. This is the push-pull regulators. Oh, there is a lot of. Yeah, this is Wendberg switching regulators. More and more complicated, more and more efficient. One of them are using for smaller currents, one of them are using for higher currents, one of them are using for higher voltages or lower voltages. Okay, so we've got a lot of topologies. This is the bridge topology, and so on and so on. Okay, so we've got a lot of examples of topology. You can see that we've got, if we can convert it as a burst of the buck or the bus bulk regulators. So you have to choose. I don't know how to advise you what to choose, because it's the different solution, different proposition what for the switching regulator. Yes, so we've got a lot of this topologies. Yes, a lot. So generally we have to choose, but we've got some tools. It's normal. We've got the tools. It is from Texas Instruments, but there are more companies that propose such a tool. This is a tool to construct, to calculate the element of the switching supplier. Yes. So let's say we choose the simplest one, and in this situation we have to put some data. So what are the values of the, let's say, with minimum input voltage and maximum, let's say with 10 volts, 12 volts as a maximum, how much current we can achieve. And in this situation, the program will calculate, yes, will calculate the elements of the switching regulators. Okay, so yes, you can see what's happened on the branches as an input, as an what's on the output. This is a voltage output capacitor, yes, and this is the current. Yes, this is typical burst situation. Yes, when it's fed by the coil. Okay, we can change what happened when the input voltage is changing. Yeah, and we can see what if we increase or decrease the load current. So we can observe what's going on the. Let's say we can see what's on this diode, and we can observe how it changes when we change the load current and the input voltage. And in this situation, we can say is the supplier is efficient for us. Yes, it is good or not. Of course, they can calculate the powers, and they calculate also period. Okay, because we can change also the switching frequency. It's 500 here, but we can change, I don't know, we can say no, it's not 400. Yes, it is. It also goes on. If we make something wrong, let's say set some smaller frequencies on the red, there are values that can be achieved. So Okay. So in this case, we did produce a power supplier that have 5 watts as an output power. Yes, it is because the efficiency is very high, so the input power is similar, of course, a bit higher, but similar to the output power. So the losses on the circuit is very small. Yes, it's just one watt or more than 1 watt on this circuit. But we can choose different topologies. Let's say which one we choose. This one. Okay, and in this case we can design more power voltage supplies. As you can see, this is typical for 1 kilowatt or half a kilowatt supplies. Yes, so this is a topology that probably is used for our computers. Yeah, in this situation, we can see that the input voltage is comes not only from batteries, but comes from the plug. So we've got higher voltages here, and we reduce it to the smaller voltages. Yes, because we set the output voltages, but we can say also 12 voltages, but we should change probably. I don't know what to change because it's more complicated, but anyway, we can change the values of the elements of the input properties, and we can design a proper power element. Okay, so we do not have to calculate all these elements by ourselves. We've got some tools to do it, but the problem is this was an element. That was an element that makes the voltage difference. Yes, so this is the element that causes that the voltage is lower or so on, but we need to control them. Okay, so now the problem is how to control the system, control the supply. So generally we've got Y reference. This is the reference voltage. This is the control objective. This is the theory of for regulators. So don't hesitate. It is just a theory. So this is, we've got a summing element here. We've got we've got some controller. This is a controller which controls the gates of the transistor, and we've got the system. Yes, this is the controller, and this is our system. In our case, this is the voltage regulator with different topology, of course. And we've got the output, V output. Okay, so generally, this is of course a transfer function. Yes, this is a transfer function for our regulator and for our system. Yes, and we should transfer function for our controller. So the transfer function is the difference between the input and output. Yes, you should remember this. Okay, so we've got a reference voltage, reference objects. We've got a summing element because if we would like to control the output voltage, yes, this is the output voltage, we should make a loopback construction. So the information from the output goes to the input, and yeah, so this is y. So we've got the difference. The e is the difference between the y and y reference. In our case, u out minus u reference. Yeah. And this, let's say, it is an error, because this is an error. This is the regulation error. So this is difference between input and the reference, output by the reference voltage in our case. So the error goes to the controller, and controller controls the system. Okay, so generally, what is the problem? Okay, so we know, let's say, we've got some transfer function. Transfer function, it is the difference between the outputs and the input. So okay, so this comes from the theory of the regulators. So in our case, we've got the y equals, this is the transfer function of our controller. Yeah, this is the transfer function of our system, for power system, and this is the transfer function for our controller. And S minus. Yeah, this comes from here, because we've got two systems with two transfer function in series, so we multiply them. So in generally, we've got GP multiplied by GC, and this is by the E, because the E is the input voltage for these two elements, but E is the reference minus Y by S. So in this case, we've got the equals GP GC 1 plus GP GC. Okay, so we can calculate the elements. Generally, we know what is the GP, because this comes from our system. So we know what is the transfer function for our topology what we used, and we achieved to calculate the elements of the control system. Yes, this is the transfer function of the control system. So, for example, for closed loop topology function, it is once again GP GC. Of course, all of them are from ADS by 1 plus Okay, so this is our first equation from the buck converter. Buck converter transfer function is equal to this. This is the buck converter. For example, if we use the buck converter, we can calculate. This is the transfer function of our not the controller, but the elements we control. Yes, this is GP. And for buck converters, in this case, we've got YS. And this is how input LC. If we use simple topology of buck converter, this is the capacitor, this is the inductor by S. LC. Okay, so this is the transfer function. Yes, this is the transfer function. We can move this function here. Yes, and then in this case we can calculate the type of GP of GC of the transfer function of the control. So in this situation we can make a general. I expect you didn't have any experience with the theory of such an element. Did you have any calculation of the automatic of the loopback construction? Can you hear me? No, you didn't have. So I'm not going to prolong this subject because maybe it's too complicated for you. But generally we will have this transfer function. Yes, this transfer function. Yes, for the whole regulator, so the regulator plus our topology, and we can calculate some elements. Yes, this is some poles. So you probably didn't have such a situation, but never mind. If you solve this equation, you can have some poles. Yes, you can. In the matter of fact, we will have 3 poles of the situation. So 0 points. Yes, so 0 the poles of these equations. So if the poles are like here, generally it is the stable situation, and because it is closed loop, so we have this error. Yes, this is the error, and if the error is higher, we've got something like this. Okay, so at the beginning we have this is the error. Yes, let's say here is the 0. This is the 0 of the error. So and in the beginning we've got the 0 output. Yes, this is the 0 output and V in as an input. So this is minus V in, and then in the regulation modes, the regulation will be like this, and we would like to achieve zero error. It means that the V out equals to V reference. Yeah, V in, this is equal to V reference. Yeah, so because we can change the elements R and C, if we use different elements, we can change the poles. So in this situation, we got a stable situation. But if we solve the transfer function and we solve and we solve them, and the situation will be in opposite side. So the poles of the equation will be like there. So the elements, the equation will be not stable. Okay, so will be something like this. Okay, so for our purpose, we need to choose a special elements for the circuit and special elements for the feedback loop controller. Yeah, this is typically the feedback the feedback loop controller. We use something which is called the PID controller. Have you heard about PID controller? Okay, no, because this is the controller which consists of three elements. One is connected with the KI. You have three elements. One is KI. KI, it is the linear element of the controller, plus this is the proportional, let's say it's a proportional element. This is K, right? This is connected with the yes, this is connected with the summing of the error and the K day, which is the derivation. This is the derivation of the error signal. And the PID controller consists of the two elements, and we need to calculate all of this control systems. Okay, so as I said before, if we solve the solution, we can changing these elements. We can change the poles of the system, and we have to choose this one, which is stable. Yes. So of course we can calculate it more and more, but maybe it's not very important for us. So generally, we should using a special controller for our circuit. We should have achieved a stability of the system, so the voltage should be stable, not a variable at the end, and we should have the rise time. It should be faster, yes, because we'd like to have the output voltage at once. Of course, it can't be set on microseconds, but it should be very fast. So we need, on the other hand, we need fast rise time and the stability, and we can choose the elements of the controller to achieve such an elements. Okay, but maybe it is for someone who is more into the theory of automatization of controlling system. Okay, so what next? We've got different topologies, so we need to choose different controller from the topologies. But this is just a part of the our system. Yes, this is just the conversion and control. Yes. So we were talking just about this element, but the real power supply needs to have more elements. For example, the first one should be the input protection. The input protection is we will use some elements to pretend the output the output elements we supply to be burned. Yes, because we protect it from the high frequencies. We can protect from high voltages. We can protect from high currents. Yes, because if something is wrong with the or the supply or the elements we supply, they should switch off the voltage supply. So the first element, it should be input protection. Then the input filtering. The input filtering is very necessary because using switching regulators, we make something what electrician don't like, because generally of course, if we use a battery, it's nothing to electrician, but if we connect it to the plug, it comes from the outside world, and then generally it comes from transformers with higher inductance properties. So if we use switching transistor, we're changing the angle between current and voltage, and in transformers it is not a very good solution because they change the efficiency of transformers. So generally we need to add some filtering system to prevent from changing the angle between the current and the voltage, especially if we are using sinusoidal voltage as an input. Okay, there is no meaning if we use a battery, because if we use battery, we start with in this point. Yes, so in this point we convert sinusoidal output voltages to the constant voltage. Yes, and we need the input protection and the input filtering. And then we've got some, of course, also the protection from our circuit. This is the protection on the DC part of the power supply, then conversion control, and then the filtering and outside protection. So it protects from something if something wrong goes on with these parts. This part should protect from higher voltages going from this part. Okay, so generally power supply is more complicated than it seems to be. So especially if we use one transistor to stabilize the voltage, and in this case we've got a lot of elements to build to calculate. Okay, so sometimes maybe it's better to use a transistor than the switch power supply on one hand, but another hand we can buy any type of DC converters just for 5, 7 or 10 zloty. So maybe it's better to buy an element which is built and to use it in our circuit. Okay, so now I would like to tell you something about the protection. Yes, some protection elements, both used from the input and output, because they are similar elements. So we've got this transient suppression devices, some transient suppression elements. They can reduce the amount of energy released as the result of over voltage spikes and surges. So as we suspect, using switching transistors, we will have some spikes, some higher voltages. So we need to reduce them. Okay, so in these sinusoidal elements, we will have some spikes coming from our coil, from our capacitors, and so on. So when we switch the signal, we will expect that we have some spikes in it. Okay, so what can we do? We've got some voltage climbing device. This is metal oxide varistor. Varistor, it means, as you know, this is just 2 diodes inside. So this varistors, this varistors prevent the over voltage across the terminal. So if the voltage is too high, if the current is, in case the current is too high, it reduces the spikes. Yes, so in our typical, without protection. Yes, without protection, we've got the spikes as on the input, they move to the output. Yes, and if we use some, we can use, of course, the filtering system, which reduces the spikes. We can reduce the spikes, or we can use this metal oxide varistor to reduce the spikes, because they cut off something which is not necessary for us. Okay. So this is the example of, let's say it's a topology. Never mind what is the kind of topology, but in the end, we've got. It is not a switching transistor, in the matter of fact, because we've got a transformer here and just a normal supply, transformer supply. So if we use this spike as an input, it comes from the filtering system and it is cut off. So there are, and this is too basic. This is the kind of filtering system. So we've got a supplier here, filtering, and our load on outside is with some protection. So this filtering system reduces the spikes, reduces the elements which are not necessary for us, and makes that our output signal is stable. Because if you remember from our oscilloscope, we've got a lot of not necessary frequencies as an output of our switching regulator. So we need to filter into to have a stable voltage. Okay, we can also use a simple solution. So we can use a Zener voltage. So if the voltage is higher than the Zener voltage, it is cut it, because current goes from the Zener voltage, and as an output we have more spikes. Yes, it's limited to the Zener value of the Zener voltage. Yes, of the device. So we can use a Zener voltage to protect the output device from higher voltages. Okay, if we are using devices which needed 2 volts, we can use yes, this is for sinusoidal suppliers. So we can, using 2 Zener diodes, we can reduce both high and low negative clamps, negative spikes. Okay. Okay, so what more? We can also move this metal oxide elements also to climb, because it comes with 2 diodes inside. Okay. We can also change it to the more complicated element. We can use a thyristor to protect our circuit, because in this case we also reduce the amount of voltage. Yes, because if the voltage here is too high, the thyristor starts conduct, and the current goes through the thyristor, not from the load. So we can reduce the spikes, reduce the voltage, which are not necessary or dangerous for our output. Okay, so generally, as you can see, to calculate, to design a proper switch supply voltage, it is not a very easy way to use to do, but we can do it, and with some experience we can produce a very efficient and very small and light and not heating elements. So of course it is up to you. It is you should have some experience, and you should first make some simulation or make some investigation what kind of topology, what kind of suppliers you should use for your devices. So if any time in the future someone will ask you to make a supplier, you can use some tools, you can use some elements we are talking about. Okay, so I think for today it's all. If you have any questions, please ask me now. Of course, I'm not going to ask you about this equation at the exam, so do not worry about the exam, because the exam, as I remember, is 11 and then 18th of the. Do you know when the exam starts?
Well, I don't know if you want to do this exam in the session time or not, but I think it's...
Yes, it's then on the session time. Not the zero exam is at the end of our course, so it's on the last lesson. But if I remember, it's the 11th and 19th of this. I don't know. I will write you down what's the time of what's the. Okay. The sessions, 19. So it's 11 and 19. I will write you down what's the time and what's the day of the exams. Okay. Any other questions?
Well, are we going to get any list of questions or not?
No, not.
Okay.
But you probably will have the opportunity to find out what was in the last year, because from your colleagues, I think it should be something similar to what was on the last year. Okay. So thank you very much and goodbye. Maybe you will say, because I can. This is. And we will see before the Christmas. No, probably. So I wish you a nice Christmas and Happy New Year, and see you in the next year.